So this time we're going to talk about section 3, and so we were talking about electron degeneracy and how that fails to form a neutron star, and so then what happens is that you get a supernova. So we're going to talk about supernovas, specifically supernova 1987A, but I want to look at several of them. So these are supernova in other galaxies. This is why supernova becomes so important to us over the next couple of chapters, because you can see a supernova as it occurs in galaxies, far away. These are, at various different distances, but you can see the bright supernova compared to an image of that galaxy either before or after the supernova. And because we can tell exactly how bright some kinds of supernova are, regardless of how far away they are, it gives us a way to measure the distance to other galaxies. And so I'm getting ahead of myself there. I want to look at several supernova, for one thing because they're just beautiful, and for another because they tell us a lot about the universe and how stars live, and all of the chemicals that come from stars. There's an old Chinese proverb, be humble for you are dung, be noble for you are stardust. I have just brutally butchered that proverb, but we are all made of stardust. And we're going to get to that a little more in just a second. So supernova 1054, so this was first observed by the Chinese, and has been observed several times since then. It's one of the most famous supernovas. It's visible in binoculars, but it does not in binoculars look like this. This is a Hubble Space Telescope image. It is 6 light years across and 6,500 light years away from us in Taurus. And towards the end of the chapter, we're going to talk about it again because there is a pulsar in there. So that's kind of cool. Here is supernova remnant 1066. This was first observed in 1066. We might be seeing a trend there that, the number for a supernova sometimes tells us when it was first observed. This is an image from the Chandra X-ray Observatory. The X-rays from the remnant are in blue. Visible light is in yellow, white, and radio emission in red. We notice that there seems to be almost a shell around the supernova. We're going to start observing those, and it gives us a clue to some of what's going on. Then we have supernova remnant 1572. This was first seen in November of 1572, and it was brighter than Venus. Quickly spotted by a young Tycho Brahe, and he observed it for more than 18 months. And so this is, once again, a Chandra X-ray composite, and they've taken the silicon, the energy from the silicon molecules and color-coded it. The blue is moving toward the Earth, and the red is silicon moving away from the Earth. That helps you see some of the very interesting three-dimensional structure to this. It's just not a round ball expanding. It's more like, you know, things poking out at you. The other colors in here represent lots of other colors, lots of other elements. Once again, we have this shell around the outside. That's the shock wave extending out and interacting with the gases of the interstellar medium as it moves out. Supernova remnant 1604. This one is very oddly shaped. It still has the fingers that are poking out, but there's also the swooshes on it. So October of 1604, this appeared as a star in Ophiuchus. It was visible for a little over a year. It is 13,000 light years away, and it is the most recent stellar explosion in the Milky Way that was visible from Earth. So this Chandra X-ray image shows us, well, the colors in here help us identify that the colors suggest that it is a type 1A white dwarf supernova because of the elements, but it also contains characteristics of a type 2 supernova, so it's kind of a confusing one. And as we, now that I have said type 1A supernova, you're going, okay, sure, what is that? So supernova are classed based on their spectra. So the very first thing is there hydrogen in the spectra or is there not? But then there's, at least 7 subclasses. I'm only going to talk about 2. Type 1A supernova. These are white dwarfs that have exceeded the Chandrasekhar limit, and they are exploding 100% of their mass into space. The star is obliterated, but remember that Chandrasekhar limit, 1.4 solar masses, so we know exactly how massive the star was. From that, we can calculate exactly how luminous the star is. This is one of the simplest ways to figure out the absolute magnitude of a star, and from there you can determine distance. Remember that distance modulus? The other major type of star supernova that we're going to talk about is type 2. And this is massive stars collapsing due to a gravitational energy event, and, boom. So those are the 2 types of major types of supernovas that we're going to talk about through the rest of the class. And so supernova 1987A, I said that, that previous one was the last supernova event in the Milky Way galaxy. 1987A is not in the Milky Way galaxy. It's located in the Large Magellanic Cloud. Okay, I will at least concede that the Large Magellanic Cloud is a dwarf galaxy orbiting the Milky Way. But anyway, so here we see an HSN image showing the event, and then a Chandra composite, and it shows us, the shock wave moving away from the explosion. So one of the interesting things about supernova 1987 is that it's recent enough that we had observed it before, and so we know which star exploded, and we have information about what that star was doing. But around 30,000 years before the red giant exploded, it expelled a ring of gas. And so as the supernova explosion the supernova explosion gases are moving much faster through space. So they have caught the gases from that were sloughed off. And in 1987, we see that the gases out here in this ring are glowing, but there's only one really bright hot spot. And then, here in 2003, there's 15 bright hot spots. So it tells us that those, supernova gases are catching the ring of gas. And as that happens, we've been able to learn a lot about the chemical composition of the original gases that were, sloughed off, and the composition of the supernova explosion. We're also learning a lot about the way things move in space, and we see all of these events, planetary nebula and supernova, that have this ring around the outside of the star. For planetary nebula, we were assuming, and we still do assume, that is the binary partner, but perhaps those have an event similar. There's still more research to be done on all of this. And then supernova 1987A, each type of supernova will have a different graph. And for 1987A, we see this hump where for a short period of time, the supernova is getting dimmer, slower than it is after 500 days. And so that 500 days is kind of important. In the spectra of 1987A, we see the characteristics for nickel-56, which is an unstable radioactive atom. It decays in approximately 5 days to cobalt-56, which is also unstable and decays in about 77 days to iron-56, which is stable. And so this hump means that after about 500 days, the brightness of the supernova that was being contributed by those radioactive decays stops, which nicely matches up with the nickel to cobalt to iron. And so it just sort of becomes added proof that these much larger elements, the bottom half of the periodic table, are being created in supernova explosions. And that's where that Chinese proverb, "Be noble, for you are made of stardust." All of the heavy elements in everything on the earth, including all of us, came from inside the core of a star. So several chapters ago, we talked about neutrinos, and so when supernova 1987A exploded, less than 0.1% of the energy appeared as visible light. 1% of the energy destroyed the star, and the rest of that was carried away by neutrinos. So we have neutrino detectors. They're these crazy huge things with this huge body of water, and the neutrino comes through and interacts with the water and lets off electrons, and so we see those electrons. Well, a total of 97 neutrinos were detected from supernova 1987A. And from them, we were able to determine that the temperature of that central explosion on the supernova was 200 billion Kelvin. Billion with a B. Yes, billion. Anyway, So up next is pulsars, and maybe I won't talk so long because I won't think they're quite so as interesting.